Can you recognize these faces? I'm sure the answer would be yes, because these all are well-known faces. But what about these faces? Your answer has to be no, because these faces are generated by AI and don't actually exist. How is this possible? Through generative adversarial networks, or GANs. When GANs were introduced in 2014 by Mr. Ian Goodfellow, it created a storm in the whole AI industry. And we can see from this graph that the cumulative numbers of research papers on GANs have increased exponentially year on year. In fact, many have called it the most interesting idea in the last 10 years of machine learning. I think enough motivation to start. Welcome to the Tech Talk series of Sigmoid. My name is Vijendra Jain and I am working as lead data scientist at Sigmoid. Today, we are going to talk about GAN, that is Generative Adversarial Networks. Let's go over to some of the key applications of GAN. First application is text-to-image translation, where GANs can translate text to image as seen here. Second is image-to-image translation, where black and white images can be transformed to colorful images. Under image-to-image translation, we can see applications for social media like generating emojis or face aging based on photographs. GANs can also be used to generate new human poses from a single pose just by taking target pose as input. This could be used by retail websites like Myntra, etc. Now let us try to understand how GANs work. So first of all, what is the problem statement here? Given a set of images, can we generate similar images? On the left hand side, you can see some real faces. On the right hand side, the faces are generated by GAN. If you think about it, this sounds almost magical because we are generating new faces out of nowhere. Now the question is, how do they do it? Well, this is achieved through two neural networks competing against each other. One is called the generator and the other one is called the discriminator. The generator acts like a cheater which tries to generate the images which are not real, and the discriminator acts like a lie detector which tries to find out if the image is real or fake. Now let's try to understand how do they compete against each other. Well, initially the generator generates the fake image which looks nowhere closer to the real image. And the discriminator easily learns to tell that it is a fake image. As the training progresses, the generator tries to generate an image which looks closer to the real image. Eventually, the generator should generate images which resemble the real data, and the discriminator fails to discriminate between the real and fake image. This is the high-level overview of the GAN system. Generator takes random input and generates the fake images. There are two inputs to the discriminator. One is the real image, which are marked as positive training dataset, and the other one is the fake images generated by the generator, which are marked as the negative training dataset. This slide shows the training of the discriminator, which is a classifier. During the discriminator training, generator loss is ignored and only the discriminator's loss is taken into account. The discriminator loss penalizes the discriminator for misclassification. The discriminator weights are updated using backpropagation from the discriminator loss. Generator tries to fool the discriminator, that is, generator tries to generate images that can be identified as fake images by the discriminator. During the generator training, generator's loss is used. The generator's weights are updated based on signals received from discriminator. Now let us talk about the loss function of GAN. This is the standard loss function of GAN, which is called min-max loss function. The generator tries to minimize this function while the discriminator tries to maximize it. You can see the specific definitions of all the parameters pointed out on the slide. During the training of GAN, the discriminator is trained to minimize the misclassification by penalizing itself for every wrong classification. This is accomplished through maximizing the loss function via gradient ascent. Meanwhile, the generator produces an output by sampling random noise, which is classified as either real or fake by the discriminator. The generator's loss is then calculated based on discriminator's classification. To achieve this, the generator utilizes the gradient descent algorithm to minimize this function. This brings us to the end of the first part of the tech talk. Thank you for watching. First of all, the problem statement that we are considering here is to generate fake faces using real face images. The dataset that we are going to use in this project is the CELEB-A dataset, which was released in 2015 by the authors from the Chinese University of Hong Kong. It has got more than 200k face images of around 10,000 unique celebrities. Here, each image size is 178 x 218 pixels. We have chosen this dataset is because of the fact that it has got large pause variations and background clutter. Now let's look at the workflow of this project. First step is to import the libraries and then import the data. After visualizing the data, next step is to transform the data so that it is ready to be fed into the model that we will define. Then GAN architecture is defined and trained. Then we look at the results and then we talk about how to evaluate GAN models. In the first step, we import the required libraries and modules here. We are using TensorFlow.keras to define and train the GAN. Since we are dealing with images here, we import the image module from PIL library. And then there are some other utility libraries taken. Next, we load the input data from the Google Drive. We randomly visualize some images from the data. As we can see that the input image size is of 178 x 218 pixels. Next, we crop each image and reshape it into 64 x 64 size because it's a common practice to have square shape images as input for CNNs. We look at the data again. We can see that now the image size is as per the requirement. Further, we normalize the pixel values between 0 to 1 because in the generator architecture, we use Sigmoid function. Out of the total 200k images, we have taken 50,000 images to train our model. This is the code to define the generator architecture. It is taken from DCGAN architecture, which takes a random vector of size 100 as an input, which is passed through a series of transport convolutions followed by batch normalization. Leaky ReLU is used in the hidden layer and Sigmoid is used in the output layer as activation functions. The final output of the generator is 64 x 64 x 3, which is the required image size. We can see that there are 3.5 million trainable parameters in our generator architecture. Now we define the discriminator architecture. This is the code to define discriminator, which is a classifier. An image of 64 x 64 x 3 is an input here, which is passed through a series of convolution operations followed by flatten operation and a dense layer at the end. Leaky ReLU is used in the hidden layer and Sigmoid is used in the output layer. The final output of the discriminator is the probability score that indicates the likelihood of the image being real. We can see that there are close to 700k trainable parameters in the discriminator network. Once we have defined the generator and discriminator architecture individually, now we define the complete GAN architecture. Here we use Adam optimizer and binary cross entropy as loss functions here. Training of GAN is not like how we train the traditional CNNs. GANs are trained alternately through an iterative process. First step is to generate the fake data while running the generator. Then the discriminator is trained on the real data marked as class 1 and the fake data marked as class 0, and the discriminator loss is captured. In this step, discriminator weights are updated. Then the generator generates fake images which are marked as class 1, that is fed to the discriminator while keeping the discriminator staining off. In this step, generator's weights are updated. This whole process is repeated for every batch pass. Hence, the discriminator tries to accurately distinguish between real and fake images, and in the second step, generator tries to fool the discriminator. That's how they compete against each other. Here is the code implementation of what we have talked about in the previous slide. We have used a batch size of 128 and total epoch 300. Here we take a random vector of length 100 from a uniform distribution as input. First, discriminator is trained and then the generator is trained for every batch pass, and we store the respective loss values for every batch. In this slide, we are going to talk about the development of the generated images as we increase the epoch. At the initial epoch, the generated images are nowhere close to the real faces, but with the subsequent epochs, the generated images are looking closer to the real images. Graph on the slide below shows the behavior of generator and discriminator loss. In GANs, the training process involves a game between generator and discriminator, making it a complex process. Hence, it is common to observe oscillations and instability in the loss values during GAN training. The loss curves may not show a consistent decreasing trend or converge to a fixed point like traditional CNNs. Finding convergence in GAN training can be challenging. It is often difficult to determine when the model has reached an optimal or desired state. In this case study, we stopped at 300 epoch due to the time and resource constraints, but one can try out more experiments like data augmentation, hyperparameter tuning, different network architectures, and training strategies to achieve the desired results. It is important to note that GAN evaluation is an ongoing research area, and there is no single correct evaluation method. Different evaluation methods have their limitations, and the choice of metrics depends on the specific GAN application and objectives. In general, there are two categories of evaluation. First is qualitative and the second is quantitative. First, under qualitative evaluation is the visual inspection, where generated images are shown to human expert for feedback. Rapid scene categorization method is generally the same, although both fake and real images are presented to human judges for a very limited amount of time, such as a fraction of a second, and then they are classified as real or fake. The nearest neighbor technique involves selecting examples of real images and locating one or more similar generated images for comparison. For quantitative evaluation, the first metric is FID score, which assesses the similarity between the distribution of real images and the generated images. Another metric is inception score, which measures the quality and diversity of the generated images by using an inception V3 classifier. Maximum mean discrepancy MMD is a statistical measure used to quantify the dissimilarity between two probability distributions. There are various other methods available for the GAN evaluation. This brings us to the end of the second part and the final part of the case study on GAN. Thank you for watching.